Welcome, this is Mrs. Nearing. This video is going to be about topic 2.4, which is metallic bonding. And then big picture, when we're looking at bond types, there's three main types of bonds. You can have covalent bonding, ionic bonding, or metallic bonding. Covalent bonding happens between nonmetals. Ionic bonding happens between a metal and a nonmetal. And then metallic bonding happens with metals. And with your metals, you have two options within metallic bonding. You can have a pure metal, like for example, pure aluminum or pure iron, or you can have an alloy like bronze or steel. Most of the metals that you encounter in your daily life are going to be alloys. These are mixtures of metals. So some things about, our bonding. A quick refresher, ionic bonding happens when you've got a metal with really low electronegativity combined with a non-metal with high electronegativity. In this type of bonding, electrons get transferred to end up with a positive metal cation and a negative non-metal anion, and that's your ionic bonding. In covalent bonding, you've got these groups of nonmetals that share electrons with each other, forming these molecules, like water molecules in this picture. And then the last one, which is our focus for today, is metallic bonding. So you have a bunch of metals together. Metals all have low ionization energies. They've got weak attraction for their electrons. So what happens in metallic bonding is a little different. There's not a transfer or like direct sharing of electrons. The atoms kind of get together and pool their valence electrons together. We say the electrons are delocalized, or that there's a sea of electrons. Here's a picture of this. So the valence electrons in metallic bonding, those valence electrons are free to move throughout the solid. So yes, they're being shared, but they're being shared in one big collective pool. Another phrase I've seen to describe it is it's like non-directional sharing. So it's non-directional, or delocalized is the other word we see, delocalized. So the electrons aren't tied down in any one particular spot. They can move freely throughout the solid. And this is what is unique about metals that allows it to conduct electricity. Because in order to conduct electricity, you need to have a movement of charged particles. And in this case, the charged particles are electrons. So the electrons can flow freely throughout your sample. So electricity can also flow freely. And within metals, we want to know about alloys, because again, most metals we encounter are actually alloys, which are mixtures. And there's two types of alloys. There's substitutional alloys and there's interstitial alloys. And just looking at these pictures, you'll notice the main difference between them is in substitutional alloys, your different metals have really similar radii. Okay, they're similar in size, similar atomic radii. And so they kind of, you can think of it as like one metal comes in and substitutes for the other, like it takes the place of another, element. Whereas in the interstitial alloy, what's happening here, like in the case of steel, your one atom has a much smaller radius than the other atom. So these ones, if we add in carbon to some iron, the carbon atoms are much smaller. They're going to fit in between the iron atoms. And that's what we call an interstitial alloy. And yeah, so substitutional alloys, you have your elements have similar atomic radii, so you just kind of substitute in. But an interstitial alloy, your one element has a much smaller radius than the other, so it fits in the spaces in between the other atoms. And for the interstitial alloys, this, if you go back to this picture, this is going to result in increased hardness. So it's going to make it harder, stronger, less ductile, so that means it's less bendable, which can be useful because sometimes we want our metals to be firm and not bendy. Like if we're trying to build a tall building, we might want our metals to be, not so malleable and not so bendy. You could also have alloys for corrosion prevention, right? Like stainless steel. That this alloy will end up with this, nice silverware that will not corrode, okay? And stainless steel is iron mixed with some chromium and nickel as well. So that chromium oxide on the surface prevents some corrosion. And yeah, here's some other examples of alloys. So brass is a substitutional alloy with copper and zinc. Notice again how these two elements have similar radii. Solder, there's lots of different solders out there. One possibility is a tin lead solder. Notice again, they have very similar radii. So these are examples of substitutional alloys when your metals have similar radii. Here's some examples of interstitial alloys like steel. So iron's got a radius of 156, carbon's like 67, so it's like less than, half the radius of iron. And then titanium carbide, similar thing happening here. So in this case, the carbon atoms are much smaller than the metal, and so they fit in the in-between spaces, and that makes these alloys much harder. Yeah. And I also want to point out, notice how carbon, if you're looking at that, you're like, wait, carbon's not a metal. And you're right. So some of these alloys will actually have some non-metals mixed into it. And that's something you notice with these interstitial ones. So sometimes carbon gets in there and gets involved in your alloys. But an alloy is a mixture that contains, mainly metal. So here's some sample questions. One thing you want to do is identify like the type of alloy. So here's an example. We got copper, tin. Notice how they have similar radii. So that looks like a substitutional alloy. Whereas this one, iron and carbon, notice a different radii there. So this one looks like interstitial. And then this last one, pewter, they all seem to have similar radii. So we're going to call that one substitutional. And you might be given some numbers like this, or you might be given, visuals to look at to try and spot which one's substitutional, which one's interstitial. Like, so you might see kind of pictures like these ones here. Or you might actually be asked to draw a picture. So let's look at a drawing one. So here's one where it says white gold is an alloy of gold, which has atomic radius of 135, and palladium, atomic radius of 140. A piece of jewelry is made from an alloy that's 75% gold and 25% palladium, and you're being asked to draw this. So we want to draw a particle level diagram using 12 atoms that match this representative, portion here. So we want 75% of our atoms to be gold, okay? And then we want 25% of them to be palladium. So that means we want, 3 of our atoms to be, palladium, and then we want 9 of them to be gold. So if you're drawing them out, I'm going to draw 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm going to show them all having pretty similar radii because this looks like it's going to be a substitutional alloy. And how do I know this? Because they're similar radii. So again, similar radii, substitutional. If one of them is a lot smaller than the other, then it's interstitial. And then I want to show that 3 of them are a different substance. Okay. And I'm going to label these ones. These ones are my palladium. And then these ones right here are going to be my gold ones. So that is what my, drawing would look like. All right. And I encourage you to, research some various alloys out there. And yeah, let me know what questions you have. Thanks.